So, good morning, teacher. Uh, this is our project about calculus 2. And to begin with, I want to introduce about our lecture, uh, which is Hoàng Hải Hà and Phùng Trọng Thực. So, our group members have two members. First one is Đặng Ngọc Hưng. ID student is 2153404, and Bùi Đại Lượng 2153555. So let's start with the project one. The theories. First one is the introduction. The method of Lagrange multiplier is a trajectory for finding the local maxima and minima of a function subject to equality constraint. Subject to the condition that one or more equations have to be satisfied exactly by the chosen values of the variables. It is named after a mathematician, Joseph Louis Lagrange. The basic idea is to convert a constraint problems into a form such that the, the derivative, the test of an unconstrained problem can be still applied. The relationship between the gradient of the function and the gradients of the constraint rather naturally lead to a reformulation of the original problem known as Lagrange function. The method can be summarized as follows. In order to find the maximum or minimum of a function fxy subject to the equality constraint gxy equal to 0 from the Lagrange function. So we have the first one, pxy lambda equal to fxy minus lambda gxy. After that, we have to find the stationary points of p condition as a function of x and the Lagrange multiplier lambda. Let m be the point that is maximum point of f. So we have the first one, px xy lambda equal to fx xy minus 2 lambda gx xy equal to 0. So we can calculate lambda right here. Lambda can be both positive and negative in this situation. So we move on to the next equation is really similar. So we move on to the next equation, which is fx and gx equal to fy and gy. I mean, they are symmetric. That's why the vector fx and fy and gx and gy must be parallel in this situation. For example, we have the first equation fxy, x squared plus y to the power 4 minus 2x minus 4y plus 15 with constraint gxy equal to x squared plus y squared minus 2 equal to 0, and pxy lambda equal to x squared plus y to the power 4 minus 2x minus 2y plus 15 minus lambda or multiply for x squared plus y squared minus 2. So the partial derivative of p, we got px equal to 2x minus 2 minus lambda multiply 2x equal to 0. So we got lambda equal to x minus 1 divided for x, and py equal 4y to the power 3 minus 4 minus lambda multiply 2y equal to 0. So we got lambda equal to 2y squared minus 2 divided y. So from equation 1 and equation 2, we got x minus 1 divided for x equal to 2 multiply y squared divide minus 4 2 divide y. Combined with the constraint x squared plus y squared minus 2 equal to 0. So we got there 2 points of x1 and y1 equal to 1 and 1. and x2, y2 equal to minus 0.23113 and minus 1.39519. And okay, so due to z1 equal to 11 and z2 equal to 24.88552, and z2 is a lot uh, a lot bigger than z1, so z1 is the minimum point and z2 is the maximum point. So we move on to demonstrate with the graph. We got MATLAB code and we have two input. The first one is we have x equal to minus 1.7, 0.1, and 3.5. And with input y coordinate is minus 2, 0.1, and 2. So we got a circle, which is the result of the equation G. In this code, we use. So we uh, look at the graph. We have the minimum point is when the fitting circle is going to touch the circle, which is formed by the equation Z achieved is the point of minimum. So we move on to the maximum point, which is under Hung is pointing at that point, and it's a maximum point. So let's move on to the result. The circle is constrained, so the contour lies is the function, and uh, we can see that the approximate point which have the coordinate at minus 0.323 and minus 1.39. The circle is taken with the contour line level 25 and the point 1.1 reach the lowest place in the contour graph. So we move on to the project to gradient descent. First, we have theories. First one, introduction. Gradient descent is an optimization to find the minimum of a function. It starts with a random point on a function and move in the negative direction of the gradient of a function to reach the local minima. The first order optimization algorithm used in machine learning, aka known as ML and deep learning here, to minimize the cost loss function linear regression. Function requirement gradient descent uh, algorithm does not work for all functions. There are two specific requirements. A function has to be differentiable. It must have a derivative for each point in its domain. Not all functions meet these criteria. Converse, for for a univariate variate function, this means that the line segment connecting two function points lies on above its curve. It does not cross it. If it does, it means that it has a local minimum, which is not a global one. We move on to the procedure. Let y equal to fx is the function we observe. Step 1, we start with we start from a random point x1, then we find radian of the function. Step 2, move in the direction of the negative of the gradient. We need to choose suitable learning rate. So we got a formula x2 equal to x1 minus and a multiple for f for function. Step 3, repeat many times to reach an acceptable local minima. Explanation. As we know that gradient vector indicates the way which the function increases fastest. So if we try going against gradient vector, we can reach the minimum point. For example, let z equal to fxy equal to 4x 4 multiply x squared minus 4xy plus 2 multiplied by y squared. We got a solution. Gradient vector of z, we got a function of f x y equal to z divided x and z divided by y equal to ax minus 4y minus 4x plus 4y. Choose the random point x1 and y1 equal to the coordinate 2 and 2, and learning rate equal to zero point 0.1. We repeat many iterations of gradient descent. So as the following below you can see, we move on to find minimum points in theory. First we got the equation of z divided by x equal to ax minus 4y by equal 0. Uh, and the equation of z divided by y equal to minus 4x plus 4y equal to 0. So x equals 0 and y are also equal to 0. So we got the under below. So we can consider delta equal to minus 4 squared minus a multiplied 4 equal to minus 16, which is smaller than 0. And the equation is must be bigger than 0. So the point O is minimum point of the function z fxy. To the conclusion, by applying gradient descent, we can find a point which is acceptable minima in comparison with theoretical point. So we have the reference below.